Hello and welcome to today's session. So, we will start from exactly where we left in the last module, continuing with the stability analysis of the common mode feedback. So, this is our fully differential amplifier where we left last time, and we are establishing the common mode DC bias for this fully differential amplifier with the help of this auxiliary amplifier or the differential amplifier with current mirror load. And we saw how these two differential pairs, they are helping us in extracting the common mode level of the fully differential amplifier and providing a feedback bias voltage for the PMOS transistors, so that an appropriate common mode voltage close to the required value Vref is established in the main amplifier. And then we look at the common mode half circuit. So, if you are looking at common mode signal or common mode DC point, we said that these two signals drain potentials are going to be close together, they are going to be exactly same if the transistors are matched and you have a common mode DC level applied over here. So, in that case, for the common mode half circuit, especially if you are talking about only the DC bias point, assume that we have a common DC level applied at both the inputs. As a result, both the drain potentials are also at the common DC point, and any signal appearing at this point is going to appear at the gate of both these PMOS transistors, and as a result both these drain potentials will also change in the same fashion because of any signal appearing over here. Therefore, for common mode analysis we tied them together, and therefore, the two PMOS transistors and the NMOS transistors were combined together to arrive at the common mode half circuit. So, if I call this M1, M2, M3, M4 and M5. So, this I can write this as M3 plus M4 and M1 plus M2 and M5. So, we are talking about DC potential. So, gates of M1 and M2 both are at DC bias point. So, I can put an AC ground over here. Likewise, the gate of M5, which is the tail current source, that is also at a DC bias point with the help of a reference current mirror, for example. So, we can put a AC ground over here as well. Now, the output of this stage, as we know, is going to the error amplifier. So, basically I can put a symbol for this error amplifier. Now, if you look at the common mode DC point, that is the both outputs over here tied together, therefore, both these potentials are also going to be same, and therefore, if I look at these two transistors, they are having the same gate, drain and source potential. Once again, therefore, I can just combine these two into a single transistor, and we know that under that condition the W by L and the ID of the combined transistor will be same as that of the other transistor. Remember, as per our earlier discussion, this was having half W by L and half ID as compared to the other transistor. So, now for the common mode operation, since these two gates are going to be combined together, we can represent it as a single device, and as a result we arrive at a configuration which is something similar to our standard diff amp with current mirror load. And we have our V out basically going to the output using the feedback signal. So, just to keep things separate, and here we have the Vref. So, here if we look at the overall operation, if we remember our analysis, if we represent this error amplifier as a symbol and then look at the terminal definition, we had said that the reference signal is at the negative terminal and this one is at the positive terminal, right. So, the actual VCM that is coming from this combined transistor, that is actually behaving like the positive terminal and Vref is the negative terminal. So, that if the VCM goes up, that means VO plus VO minus by 2 goes up, this should also go up, and as a result the PMOS gate voltage should go up and should bring the common mode voltage down. So, by our definition, the actual common mode signal coming from the differential amplifier is applied to the positive terminal and the reference was applied at the negative terminal. But now for this feedback analysis, we have another stage added over here if you look at it. So, this is basically inverting stage. So, if we break the loop considering the input signal to be the Vref and see how the signal is propagated through the loop, we will see that with respect to Vref, this one is a negative output definitely, because if you increase the Vref, this reduces the inverting terminal with respect to Vref. But after that you have another inverting stage. So, this is something like a common source stage where M3 plus M4 is acting like the input device, and therefore, we are going to have an another inversion over here. So, with respect to Vref, we will get a non-inverting gain till this point. From here to here, one inversion, and then back after tracing the loop from M3 M4 gate to the drain, another inversion. Therefore, from Vref to this point, we have a non-inverting gain. Therefore, for this two stage combined together, we can say that this is a overall non-inverting terminal on which you are applying the input, and the feedback signal, as we have seen yesterday, can be seen as voltage sampling. So, whatever final voltage is coming over here, that is directly applied as the feedback voltage on the other terminal of the differential amplifier, which is effectively the negative terminal. So, here is our sampling network, which is sampling the output voltage produced by the second stage, and it is applying that sampled output voltage to the effectively inverting terminal of this overall two stage amplifier formed with the help of the main differential amplifier and the common mode feedback amplifier. So, now if we therefore open this loop, assuming this sampling factor to be unity, we can say that you are having a input signal applied at the positive terminal, you are having the voltage, the non-inverting amplified voltage signal coming back, which is finally applied at the negative terminal. So, when you increase this input signal Vref in the positive direction, the VO also goes up, but it is applied to the negative terminal, therefore, it is subtracting from the applied input. So, basically we are having a series connectivity at the input, the feedback voltage is effectively being subtracted from the applied input signal Vref, and at the output whatever VO is produced, we are directly sampling it using the unity beta factor and applying it to the negative terminal. Therefore, you have a shunt connection at the output, therefore, we have a series shunt configuration, and while opening the loop for a series shunt configuration, we can see that for the beta network over here, if you are looking at the output port of the beta network, the overall impedance seen looking into the output port, irrespective of the overall impedance seen looking into the input port of the feedback network, the configuration is shunt, and therefore, we will be applying a overall ground terminal over here. So, let us draw the open loop configuration. Looking from the output port of the feedback network, the other terminal is shunt, and therefore, as per our earlier discussions on feedback topologies, in order to open the loop, the shunt terminal will be grounded, and therefore, you just have an AC ground established at this point effectively while opening the loop. And likewise, if I am looking at the feedback network from the input side, remember this is the input side of the feedback network, because here you are sampling the output voltage, and with a unity gain you are transferring it to the output point. So, if I am looking at the input port of the feedback network, once again at the output port we have series connection, and for series connection we know that we need to open circuit that point, and therefore, once again looking from the input port of the feedback network, we will just open circuit this point, and as a result you will have open terminal coming at the final port. So, as a result we can draw the equivalent open circuit for this feedback amplifier. So, as we said, looking into the input port of the feedback network, other end is series connection. As a result, we open circuit it. So, we are left with an open circuit over here, and on the we have the Vref, which we are assuming as the input signal, and the bias point, all the DC connections, DC bias point set to AC ground. Once again, while looking into the output port of the feedback network, the other terminal is shunt connection. We are sampling the output voltage. So, looking into the output port of the feedback network, the input terminal was having shunt connection. Therefore, we will just put a ground over there. Therefore, here we will just put an AC ground. So, this is an equivalent open loop circuit for corresponding to the common mode feedback loop. And in order to find out the stability, we need to look at the overall loop gain starting from the input point coming back to the final output over here. We are going to calculate the overall loop gain and find out the critical poles in the circuit to arrive at the overall frequency response. So, let us first look at the loop gain. So, for the first stage, we have our differential amplifier constituted by the input transistors. I can name them, say M6, this is the combined, I would say M6 plus M7, M8, M9 and M10, and call this M11. So, the loop gain will include the gain of the first stage from the input to the output over here, and then finally, the second stage from the input to the output over here. So, for the first stage, we know that the gain of this differential amplifier from the input to the output is minus GM RO by 2. Here the GM will belong to the input pair GM8 for instance, and RO will belong to the M8 and M10. So, if I assume that RO of M8 and M10 are almost equal, then I can say RO10 parallel RO8 divided by times GM is going to be the gain of the first stage. So, that is pretty straightforward as we have done it for the differential amplifier with current mirror load earlier. Now, the gain from input of the second stage to the output of the second stage, once again this is something like a common source amplifier. So, with respect to AC analysis, these terminals are AC ground. You are having the input at the gate of the PMOS and you are taking the output at the drain of the PMOS. You are having an effective load resistance over here. So, this is something like a common source amplifier with PMOS as the input device with certain load connected. What is the load impedance if we look into the drain of this device? So, we know that whenever we have this kind of stacking of transistors, the stacked transistors boost the overall impedance looking into the drain. So, here we have overall GM, we can call it GM1 plus 2 times the overall RO. Now, what is the RO of the combined transistor if we want to be exact? So, total current flowing through the pair of course is just double the RO of the individual transistor as we know, and as a result the RO of each of these is going to be or RO of the combined transistor is going to be half of the RO of the individual ones. So, I can just write down RO by 2, and in fact this GM1 plus 2 we can write it down as 2 GM, and this times the RO of M5, so RO 5. So, this is effectively the overall small signal resistance looking into the drain. So, we get a factor of GM RO square. So, whenever we have stacked transistors looking into the drain of the NMOS, we will have overall impedance given by the resistance in the source, that is RO multiplied by GM RO of the stacked transistor. So, GM RO of this transistor multiplied by RO of the bottom transistor gives us the impedance over here. So, this is your R down if I call it R down, and therefore, if I am looking at the PMOS transistor over here, it has its small signal resistance from drain to source as well, RO, and therefore, the overall gain of this stage will be GM3 plus 4. So, I can call it 2 times GM times the overall parallel combination of R down parallel R up. So, here you have the small signal resistance looking up, R up. So, the overall small signal resistance coming at this output node is a parallel combination of R up and R down. So, I can write this down as R up parallel R down, and we know that R down in this case is much larger, GM RO square, GM RO times RO, where R up is just RO. As a result, the R up will be the dominating factor, the smaller one will be the dominating factor. As a result, I can just write down the overall gain as 2 GM times RO, and as a result, the total gain combined A1 A2 is having GM RO square expression. So, overall loop gain A1 A2 is GM RO square expression as we expect. So, ultimately we have two amplifier stages, both of them active load. So, we expect that the final expression should have GM RO square term coming up. Now, once we have the gain, in order to find out the overall frequency response for the open loop amplifier, we need to calculate the critical poles, and we need to identify which are the circuit nodes at which we are going to expect critical low frequency poles, which are going to determine the cutoff frequency of my open loop amplifier. So, from our previous discussion on the differential amplifier with current mirror load, we know that this particular amplifier offers a critical pole at the output node, because here the overall impedance is highest, that is RO by 2. At the other node, the overall impedance is significantly smaller, it is just given by 1 upon GM of the direct connected device. As a result, this is the one which is going to offer critical pole for the first stage. And if you look at the second stage, we can see two circuit nodes, first one over here and second one the output node. If I consider the lower node over here, here we know that the overall small signal impedance will be given by RO5 parallel the impedance looking upward. Now, the impedance looking upward into the source of this combined transistor M1 plus M2 with a single PMOS active load is going to be of the order of 2 upon GM. So, it is of the order of 1 upon GM, and therefore, the impedance looking upward into the source of this NMOS is significantly smaller. As a result, this pole, the RC time constant is going to be small. As a result, the pole frequency is going to be pretty high. So, we did not worry about this particular node. However, we have just seen that the overall impedance at this node is of the order of RO, and therefore, it is of similar order or similar magnitude as compared to the pole over here. Therefore, this is the second, I would say, critical node at which we are going to have a critical pole. So, we have identified the two nodes, one over here and the second node over here, where we are going to have critical poles. As of now, we cannot confidently say which one is going to be the dominant one, whether one of these are going to be smaller or the other one is going to be larger. That cannot be said in a straightforward fashion, but both of them can be comparable. So, if we need to find out the expression for the poles at this point, we need to figure out the overall parasitic capacitances. So, basically following the standard procedure that we have learned earlier for single stage amplifier and differential amplifier, we can figure out the overall parasitic capacitance at this node and the second node by counting the contribution of all the transistors. Wherever we need to apply Miller effect, we need to apply the Miller effect to break down the capacitances between this node and some other terminals in the signal path, and in some cases the capacitance directly appear between this particular node and the AC ground. So, accounting for all those, we can figure out the overall parasitic capacitance between this particular node 1 and AC ground, and that will give me total C1. Likewise, at the output node, we can find out the total parasitic capacitance, the total effective parasitic capacitance between the output node and AC ground by counting the contribution of parasitic capacitances for all the transistors, and that is going to count as C2. And we also have the R equivalent at these 2 points. I will call this R1 and R2, and that is how we are going to get the two poles P1 and P2 at these 2 points. And once we have these 2 poles, and assuming that other circuit poles like the pole over here, like the pole at the source of M1 plus M2, they are at sufficiently high frequency. So, if we make that assumption and for the time being consider that these are the only two dominant poles and all other poles in the circuit are at sufficiently high frequency, I can draw the overall frequency response assuming only two critical poles in the circuit. So, let us do that. So, the magnitude response for a two pole system at low frequency, you have an overall gain given by A naught, which we have just found out, and we have two critical poles P1. After the first pole, we know that the magnitude drops with minus 20 dB per decade, and you have the second pole P2, after which the magnitude drops with minus 40 dB per decade. So, we have and likewise, if we talk about the phase response, so at low frequency we start with overall 0 phase. From input to the final output we have a 0 phase. Remember, there is a -1 term in the loop coming because the final output signal is applied at the inverting terminal. So, that gives automatically a -1 factor and hence 180 degree phase shift across the loop. So, effectively what we are having is 180 degree phase shift is already available. So, we are keeping that as a constant factor. Apart from that, if you look at the signal phase from input to output, that is starting from the very low frequency, ideally it should be at 0. So, we will start at 0 and we know that immediately after the first pole it reaches 90 degree, and immediately after the second pole it drops down and approaches 180 degree, provided you have the third pole lying somewhere close, it will approach 180 degree pretty fast. So, depending upon how close is the third pole. So, if you do not have the third pole, we know that it will asymptotically reach 180 degree at very high frequency. If you have a third pole lying somewhere close, then it will quickly reach or touch 180 degree or go for the negative as well. So, this is the overall shape of the frequency response we expect. And now, in order to get a stable response, we have discussed earlier that we need to ensure a good phase margin, at least around 45 degree of phase margin, so that in the overall closed loop response we do not have any ringing, and with respect to parameter variations, with respect to process variations also we have enough margin. So, we need to make sure that at the 0 dB crossing point, at the frequency at which the gain drops to 0 dB, that is unity gain frequency, the phase is sufficiently lower than 180 degree. Lower means magnitude point of view, it is lower than 180 degree or more positive than minus 180 degree. So, if we draw the marks, here you have minus 90 degree and far away from P2 you are reaching or approaching minus 180 degree. So, we would like to make sure that at the 0 dB crossing frequency, that is the frequency at which the gain drops to unity, the phase is sufficiently positive, sufficiently higher than minus 180 degree. And in strict sense, if we want to achieve a phase margin of exactly 45 degree, we need to make sure that the frequency at which the 0 dB gain occurs, the phase is exactly 135 degree. So, also we know that what is the frequency at which the phase reaches exactly 135 degree in a two pole system, that is a P2. The first pole we have exactly phase shift of 45 degree, far away from P1 90 degree, exactly at P2 we have around 135 degree, provided the third pole is far away. So, at P2 I have an phase which is close to minus 135 degree, and as a result I would like to have my 0 dB crossing point at P2. So, I would like to make sure that my gain drops to 0 dB by the frequency P2. So, this should be the 0 dB point. And in order to achieve this condition, we know the criteria that we need to apply. We need to make sure that omega 0 dB is our second pole P2 in the system, and also we have seen that omega 0 dB can be expressed as A naught times the P1, because we have, after immediately after P1, we know that for a 2-pole system, the overall expression can be expressed at 1 upon S upon P1, 1 plus S upon P2, and in this region in between P1 and P2, this expression reduces to, between P1 and P2, this expression reduces to A naught upon S upon P1, because between P1 and P2, you have S or the omega, which is much greater than P1. We are assuming that P2 is much higher than P1, and you are at omega or a frequency which is much higher than P1. As a result, you can ignore this one with respect to S upon P1, and hence we are left with only the S upon P1 term from the first factor. Second factor, we are assuming that the omega is still much lower than P2. So, the omega is still much lower than P2. As a result, S upon P2 can be ignored with respect to the 1 over here, and as a result, the second factor just gives me unity, and as a result, I have A naught upon S upon P1 left in this particular region. And if I assume that this expression is valid till I approach P2, it is just an approximation. So, we can say that at the particular frequency P2, we are having the overall gain magnitude given by A naught P2 upon P1, and that should be equal to 1. So, we need to have A naught P2 upon P1 equal to 1, and that gives me the relationship that the overall 0 dB point that should be equal to P2, and we have the omega 0 dB given by A naught P1, because in order to equate this to 1, we need to have omega equal to P1 times A naught. So, omega at which the gain touches unity is going to be given by A naught times P1. So, this is the relationship we need to achieve in order to achieve a phase margin of 45 degree in our overall open loop amplifier. Now, to do that, we need to make sure that the pole given by P2 is sufficiently higher than P1. We can see that the requirement is that P2 should be A naught times P1, and as a result, we need to make sure that the one of the poles, say P1, is brought sufficiently lower. It is pushed down to a sufficiently low frequency by a factor of A naught approximately, so that we can have sufficiently good phase margin. And we will see the method to do that. As we have seen earlier, one of the common method to achieve such splitting of pole or pushing of one of the critical pole towards low frequency is Miller effect. So, we can intentionally add a capacitance between two circuit nodes, so that at one of the circuit nodes the overall capacitance, because of the Miller multiplication, becomes too high, and as a result of that the pole at that particular node is pushed to very low frequency. So, in this particular open loop case, for example, if I want to push the node at 1 to low frequency, I can imagine putting a cap between this node, a compensation cap CC between the node 1 and node 2, as a result of which we are having a overall gain between this point and the output given by A2 that we have just written over here, and the result what we expect is the C1 CC 1, which is basically the equivalent capacitance coming because of this CC at the node 1 will be A2 times CC, and as a result the first node over here will be experiencing a large cap, and as a result we can try to push the capacitance over here to a much lower frequency. On the other hand, the capacitance over here, because of the applied Miller effect in the forward path, the capacitance over here will be still close to CC, because in the reverse direction we will have the factor of 1 minus 1 upon A, where A is large. So, we can ignore that, and as a result we will just be having capacitor CC coming at this node, which is much smaller than A2 times CC. So, here we can see that by Miller multiplication we can try to push the node P1 to a much lower frequency. And the second factor that also can help us in achieving further splitting is the overall reduction in the impedance between the gate of the PMOS transistor and the output node at higher frequency. So, as we will see in one of our another example that we are going to take, sufficiently large capacitor connected between the gate of the PMOS transistor and the output node, it produces a kind of low impedance path between the gate and the output at higher frequency, maybe close to P2, as a result of which the impedance looking into the output point over here becomes smaller. So, let us look into that factor in the next module, and we will try to see how the CC can help us in achieving pole splitting. At one side, it helps us in pushing the pole 1 at towards lower frequency. At the same time, it can also help us in pushing the second pole at the node 2 towards higher frequency, and hence achieve a good phase margin. And the same concepts similar concepts will be applied in case of the compensation for differential operation as well. So, let us do that.
So, why are we choosing 45 degree as phase margin?
45 degree is a safe phase margin for which in the overall transient response you do not get enough ringing. If you have 45 is a phase margin lower than 45 degree, using time domain analysis, it can be shown that it will lead to ringing in the closed loop response. If you are putting a step input at the loop, it will give you a ringing response at the output.
Then why aren't we choosing 60 degrees or
60 degrees is even better, but the design becomes more challenging, compensation becomes more challenging. So, 45 degree is an acceptable number.
So, for one stage amplifier we can do this analysis, but if there is multiple stages, then how we analysis phase margin and other things, because it can be possible that for one stage single
so ultimately you have to make one of the poles dominant poles, which is much lower frequency as compared to the other. So, in any case, even if you have 3 stages, so ultimately target will be to choose one of the nodes which can be made the dominant pole. You can push it towards much lower frequency conveniently. So, that will become our dominant pole. And if there are other poles, but they are sufficiently higher frequency than this one, then it is okay, you can still meet the phase margin. For example, in this case, you can if you want to further improve the phase margin, you can try to make the impedance of the diff amp pretty high. So, if you want to say make the RO of the diff amp pretty large by just reducing the bias current and increasing larger channel length over here, in that case the RO over here will also become large, and apart from CC you also have a significantly larger RO as compared to the main amplifier. So, that way also you can make this dominant. So, to begin with, I have assumed that okay, the ROs of this stage are similar to the RO of this stage, but that may not be necessary. So, you can intentionally make the RO of this stage much larger by applying larger channel length and having even much lower bias current in this stage, and that will basically here noise constraint are also less critical. Main differential amplifier, you have noise constraint because of which you cannot really reduce the bias current too much, but in the common mode feedback amplifier it will be little less critical because whatever noise comes, it comes in the common mode. So, because of that you can reduce the bias current of this one more aggressively, and you can apply longer channel length as well, so that the RO of this stage becomes the dominant one. That will help you in pushing the pole 1 to low frequency.
Sir, why you are not simply adding the compensation capacitor between node 1 and ground?
Because you will not get similar compensation and multiplication, you will need much larger capacitance in that case.
Okay, yeah.
So, capacitance is area hungry. If you want to exploit major capacitance, that will help you save area. Otherwise, you will have to go for much larger C. Okay, we will resume the discussion.